Okay, so let's get started here. Just a second. All right. So today we are going to start a new topic, which is distributed file systems. And we'll spend today's class and the next class talking about file systems, distributed storage, and so on. What I'll do today is start with the basics, very quick refresher of file system concepts that presumably all of you know from an undergraduate class in operating systems. But for those of you who don't have that background or may have forgotten, I'll just review those concepts quickly, and then we can get into the distributed file systems issues. And most of the class, we are going to focus on a case study of one file system specifically called NFS, or network file system. Okay? That's the most basic one, very common in Unix, Linux environments. And then next time we'll look at more advanced distributed file systems ranging from CODA, XFS, HDFS, which is Hadoop file system, other types of storage systems, and so on. Okay, so that's the agenda for this class and next time. So let's talk about file systems basics. So what is a file? Okay, you all know what a file is. You use it on your computers. But here's a definition. Okay, file is a named collection of logically related data. Okay, so it's basically a container of data. Okay, and it has a name that is typically assigned by a human so that you can go back to that piece of data at a later time. Okay, what you put on the file is basically up to you. It could be anything from a source code or a document, or it could be a binary file, and so on. Okay? Now, in the case of the Unix file system, it is this collection of data is essentially uninterpreted by the file system, which means that the file system doesn't care or is not aware of what is inside the file. So the file types are not known to the file system. Okay, but there are other file systems that actually know about what type of data is supposed to be in the file, and you can use that information in certain ways. Okay? Now, what does the file system do? Okay, so essentially it takes these concepts of files and it provides a logical view of data and storage function. Okay, so is your computer or your mobile device essentially has some disks or storage space. Okay? As a user, you don't want to deal with low-level details of where to put certain information and so on. You just want to create files and manipulate files and let the OS, and in this case, the file system, take care of where it is stored, how it is organized, and so on and so forth. Okay? So essentially, you get this logical view of what is on your storage device, and you see this concept of files and folders and things of that sort that are hierarchically organized, and the file system takes care of how to map this to the underlying storage device. Okay, so in that sense, you get a more user-friendly interface than having to deal with low-level interfaces that are exported by disk, which are block numbers and so on. You don't really deal with it as a user. The OS takes care of it. Okay, so and it provides you the ability to create content in terms of files, modify them, organize them, and so on. It allows you to share files across users using concepts of either permissions or access control lists, which we will get to. Okay, and it provides protection where data that you don't want to share, you can prevent others from taking a look at it. Right? So if there are multiple users sharing a machine, you can essentially protect your data and not share it. And if you want to share certain files, you can do that as well. Okay, so essentially, from a Unix file system perspective, now there are many types of file systems, right? Windows has its own, Mac OS has its own, Unix and Linux have their own. They by and large give the same higher level interface, but how they are built and what they do internally differs in some ways. Okay? Now, as far as Unix is concerned, many Unix file systems, these in Linux, you might have the ext3 file system, ext4 file system, and so on. Okay? So what these file systems do is they treat a file as a linear array of bytes. Okay? A file is a collection of bytes. You do not interpret what type of file it is, what's the structure of the data is. So a Word document looks like an array of bytes. A binary file looks like an array of bytes. A text document looks like an array. A text file looks like an array of bytes. So you don't actually distinguish between what type of data it is. You just treat the data as if it's just bits and bytes, and you just store essentially bytes in files. Okay, so you don't have structure, you don't have file types, and so on. Okay, now contrast this with something like the Windows NTFS, where the file system actually knows about file types. So, and even Mac OS has file systems that actually track what type of file it is. Okay, what do you do with file information? So, for example, very simple example is when you are when you have maybe a Windows or a Mac, and you double click on a file, it basically knows the file type and opens that file in the right type of application. So if you double click on a Word document, it opens it in Word. Okay, to do that, it needs to know what type of file it is. If you just treated it as a linear array of bytes, you don't know what type of file it is. So how to open it is not known. Right? So keeping file types gives you some advantages. Okay? And some operating systems have that information in their file systems, and some don't. Okay? That's something you want to keep in mind. Now, files can be organized into directories or folders. Okay? And essentially, from the file system's perspective, a directory is simply a table. Okay? It's a table of all the files or other directories that are contained in it. Okay, so that's all there is in a directory. Okay, so basically, if you create a directory with 3 files, the directory structure that the file system keeps track of essentially can be thought of as a table with the list of those files. Okay, there could be other directories also, and essentially a pointer to those files so that you can go and open those files. Okay, so it's a way to organize or group files into larger structures. Okay, and then this entire file system, okay, is essentially a directed acyclic graph or a DAG, starting with the root directory or the root folder, which has some number of directories. It might have subdirectories and so on. So if you look at the entire structure, okay, it essentially looks like a tree. But because you can actually have pointers going back and forth, it's technically a DAG, not really a tree. Okay, because you can have essentially soft links or what are called shortcuts in Windows and so on. Okay, that essentially makes it look like a DAG. Okay, if you didn't have that, it would actually be a tree structure. Okay, with a root directory and then essentially subdirectories and folders in them. Okay, so your files are organized, file systems organize files in a hierarchical fashion that is defined by the structure of the file system, okay, which is essentially a DAG. Okay, any questions on this? Because just quick recap, because not new material that I'm trying to present yet. We'll get to the distributed file system concept. Okay, now as I mentioned, a directory is a table. Okay, what is stored in that table, essentially each row can be thought of as a file name and essentially an inode number, and inode is the metadata for that file. So a directory has 3 files. You will have file foo. There will be an inode number which will say this is how you access that file by going to that inode, or that's essentially the metadata for the file. And then you essentially have something called a device number, which is what device is that file stored on. Is it a solid state disk, regular disk, USB drive? So your file system can be on different kinds of hardware devices. Your directory will store some information about it. Okay. Now, the thing you want to keep in mind is a file system has 2 types of information. It has data, which are all your files and directories, and you have metadata. Okay. Metadata is information about the data itself. Okay. So every file system will have 2 types of information. There's going to be metadata, which allows you to access the data. Okay, and so you will have essentially these 2 types of information. In case of Unix file system, the index nodes or the inodes are essentially all of your metadata. Okay, they store information about other files and folders themselves. Okay, and the way the file system is organized on disk is the metadata for all your files are stored in a well-known location, which is essentially called a super block. Okay, and the files can be stored on any other location. Okay, so there is some part of your disk that is reserved for keeping track of metadata information, and then the rest of the disk is what is going to store the actual files that you're going to create on it. Okay, the reason you do this is when the user is going to access the file, you need to know where the blocks of the file are stored. Okay, the blocks of the file can be spread anywhere on disk. your metadata or the index node is going to keep track of where all the blocks are. But to open the file, you first need to access the metadata. Okay? So you need to know where to find this metadata. Okay? And so since it's kept in a special location, all the inodes are there, that makes it easier to actually track it down. Okay? I'll say something more about that, but that's the reason you have a special location to keep your metadata. Question? Okay, question is the point that is made here is directories may not be shared, but files may be shared. Is that across users? That's your question. No, here sharing is actually in terms of creating soft links or hard links. Okay, so a hard link essentially gives two names for the same file. So you can actually have two files into completely different directories that are essentially pointing to the same content. So you can access the file as /user/foo, or you can say /local/bar. Okay, because you made a hard link, both of them are two names for this exactly the same file. Okay, this is why it's a DAG, because if you think about it now, those two names are actually pointing to the same object. Okay, now you can do this for files, but many file systems prevent you from doing this for a directory. So you cannot actually create hard links for directories. You can create something called soft links. And the reason is, if you allow hard links, you can create cycles in the graph. Okay, I can have a directory be the same as a directory higher up in the root structure. That creates a loop. Yeah, having loops in directory structures are bad, because then when you do things like search, your search will not terminate because it will just sit in an infinite loop. Okay, we will try to go down the file hierarchy and then come back up and so on. So you prohibit that from even happening. Okay, this is why you will essentially, by shared, it is essentially saying that you cannot create hard links. Okay, any other questions? Okay. So very quickly, what does an inode structure look like? This is essentially the metadata for the file. Okay? What should be in the metadata? Okay, so you can think about who's the owner of the file. Okay, what is the size of the file? What was the time the file was created? The last access time, last modified time. So all of the information that you see when you actually look at a directory. So you will see the name of the file. You will see, so name of the file is stored in the metadata. It's not stored in the file itself. This file itself has the content of the file, not other information. Owner of the file, permissions on the file, access time of the file, creation time. All of this is going to be stored in the metadata. Okay, but the most important part is essentially pointers to where the blocks of the file are themselves stored. Right? Because you need to know where is block 1, where is block 2, where is block 3, and so on. So you will essentially, in the metadata, have a table. In this case, the index structure, which is why it's called an inode or an index node, index structure that allows you to access blocks of the file. Okay, and here you have a multi-level index structure in case of Unix, where the first 12 blocks, 12 pointers of this table are direct pointers to pointers that actually point to data blocks. So if you want block 1, you look at the first entry here, that tells you a block number on this. So you will basically, if you go to that block number, that is where the first block will be stored. You look at the second entry here, it'll have a block address. You go to that address on this, that will give you the second block and so on. And they don't need to be contiguous. Okay? The blocks can be spread across. The file is actually not stored contiguously on disk. It will be partitioned into blocks, and blocks are stored wherever you want. Okay? So this happens for the first 12 entries. Okay? If the file is larger than 12 disk blocks, the 13th address here is not pointing directly to a block, but it points to another index structure that has actual pointers. So it is one level of indirection that you added. Okay, so this will point to a disk block, but that disk block is not actually a data block. It is another index block. So it will have another set of pointers. Okay, so in this case, you might have another 1024 pointers. That disk block can hold another 1000 pointers. So you can have another 1000 blocks in that file. But to access those blocks, you have to first get to the 13th address here, get that disk block, and then find each pointer and then go access it. Okay. Now, if the file is larger than 12 plus 1024 blocks, you go to the 14th address here. Okay. And that 14th address will have two levels of indirection. Okay, that first pointer will point to a disk block. That disk block will point to another two disk blocks, and those will actually point to an index structure. Okay, and then you have triple indirect, which is the last one address. Okay, so this will make the index structure look like a multi-level structure where the levels of indirection grow as the file size grows. Okay, I'm going to draw a very quick picture here to show how this works. So this is our inode. Okay, so this is a block, right? So you have certain pointers that are just pointing to disk block. So this is address I, address J, address K, and so on. So you'll have 12 of those. Okay, and then the first level indirect, the way it will look is so what you will do is you will have this. So these will themselves point to blocks. Okay, that's one level of indirection. Okay, and then you will have another one that will point to disk blocks that will themselves point to disk blocks. Okay, there's two levels of indirection. And then you have another one that's triple, where you have this goes here, this goes here, that points to disk blocks. Okay. Yes, your question. I'm sorry, what's the question?
So the starting block number 15 can have.
Just one second. Let me go back to the slide. Okay, hold on. Yeah. Okay, what's your question now? So there are 15 entries. Okay, 0 to 14. 12 are first 12 are actually direct blocks. 30, you have to count from 0. Okay, computer scientists always count from 0, not from 1. Okay, so there are 15 of these. First 12 are direct blocks, one single indirect, double indirect, triple indirect. Okay, so that gives you a maximum limit on the file size. Okay, the maximum number of blocks you can ever store in this file system is going to be 12 plus essentially 1024 blocks in the first indirect, 1024 square blocks in the double, 1024 cube blocks in the triple. Okay, that's a maximum size, 12 plus 1024 plus 1024 square plus 1024 cube. Okay, so this file system can't store a file larger than. Of course, if you want to make the file even bigger, you can add one more entry, and that can be another quadruple indirect or something like that. Okay, is that clear? That's essentially what a Unix file system structure looks like. Any questions here? Okay, so now with that very quick background, let's move to distributed file system. Okay, so here we are assuming that the file system essentially can, by distributed, we mean one of two things typically. Okay, first is that a client machine can access files stored on a different machine altogether. Okay, typically your files are stored locally on your disk, on your laptop, or on your phone, and so on. Okay, if you have the ability to access file on another machine, you essentially have a distributed file system. Okay, that's one way to think about it. Another way to think about it is that the distributed file system, or the server part of the distributed file system, is not a single machine, but it itself could be multiple machines. Right? So your files are themselves distributed across multiple machines. Collectively, that forms your file system. So a client will access a file. Sometimes it goes to server 1 to get some part of it. Sometimes it goes to server 2, and so on. Okay? That's another way to think about a distributed file system. Initially and today, specifically, we look at the first interpretation. How do clients access files that are stored on another machine? Okay. Now, in today's world of cloud computing, you already have cloud storage that gives you some idea, right? You store your files somewhere on the cloud in Google Drive or OneDrive or Dropbox. Okay. So that's essentially an extension of this idea where there are client machines that are accessing remote files. In this case, the remote file is actually stored on a cloud server. Okay? But you can also have remote files that are stored on another machine in your network and access it, and that still gives you a distributed file system. The server doesn't have to be in the cloud. The more traditional distributed file system, you just have a server machine that has a large disk. It stores all your files and you can access it remotely. Okay, so that's essentially what we want to look at. So in this case, we have a file server, which is a machine that stores all your file, and there's a file service that machine actually exports and service or an interface that allows other clients, other machines to access files. So that's the API. Okay, we'll see that NFS uses RPCs. Okay? So essentially, if your machine wants to access a file stored on an NFS server, you just make RPC request for files. You can send a read request as an RPC. You can send a write request and so on. Similar to read and write requests, you're going to make your local disk, except that these requests go as RPC requests to the file server. File server executes them and sends you back results. Okay, so that's what we want to look at. Okay, so we look at essentially the file service. There's also a directory service that allows you to have a directory structure on remote machines and so on. Okay, which we will not look at in that much detail. Okay, so here are two ways to implement remote access to files. Okay, so in this case, you have a client machine. Okay, the disk that you're accessing is on another machine, remote machine, which is the server. Okay, this is the very simplest network or distributed file system. Okay, clearly you can have many clients that are accessing, and there can be many servers that are collectively implementing. Here's one client and one server, but there are two models. Okay? The first model is called the remote access model, which is shown in this first picture, where when the client needs to access anything on the server, all requests are actually sent to the server. In case of NFS, they're sent as RPC requests. Okay, so server actually has an RPC implementation that's listening to this request. Requests come, it does whatever is requested on the files that are stored on disk, sends back results. Okay? That's your remote access model where the work is done at the server. Okay? The other one is called the upload-download model. In this case, the file is still stored on the server, but when the client tries to access it, the server provides an entire copy of that file to the client. At this point, the client has a local copy of the file. All subsequent accesses are actually made on the local copy. Okay? And then eventually, or in some based on what consistency model is implemented, those changes are sent back to the server. Okay? But there may be a period of time where once the file is brought over, all accesses are local. Okay? So that means you might modify it. Server still hasn't seen those modifications. If another client tries to access that same file, it may see an older version. Depends on the consistency model, but you could have scenarios where it's not consistent with the most sent copy, which is actually on the client in this case. Right? So you can see that there are some advantages and disadvantages of the approach. Okay, either approach. So in this case, essentially, you have all the operations being performed on the server. So consistency is easy. If one client makes an update to the file, another client tries to access the file, it will immediately see that update because all the changes are always made at the server. Okay. In this case, you have to decide what consistency model you want. Okay, because changes may be, you bring a copy of the file over, you make local changes, there may be a delay before the changes are propagated back to the server. Until then, the copy at the server is out of date. Another client tries to access it, and you will have an out-of-date version that you're supplying to that client because there's cache consistency issue. Okay. Having said that, the upload-download model gives you strictly better performance for reads and writes than the remote access model. Is it clear why? So where are the reads and writes going once you fetch the file? They are going to a local machine, right? So if my laptop opens a file on a server, you bring a copy, entire copy, and now it's here. So all my subsequent reads and writes are local. In this case, every read and write is a RPC operation. It has to be sent over a network to a remote machine. So clearly, local accesses would be faster than remote accesses. Okay, so there is a higher overhead initially because you're copying the entire file. But once you do that, all accesses, subsequent accesses are local. Okay. Here, every time you do any operation on the file, you have to send it to the server. Okay. So you have these advantages and disadvantages. Here, since all requests are going to the server may get overloaded because every read and write request is serviced by the server. Here, it's a little more scalable because only the initial download and then the subsequent upload is handled by the server. All operations in between are handled locally by the client machine. Okay, so that's essentially going to give you a little better functionality and so on. Okay. You will see that there is actually reason to keep state if you're going to keep open the file and so on. I'll come back to this notion of stateful and stateless once we get into NFS a little more, because it's easier to explain that, okay, for either of these models. Are there any questions here? Okay, these are the two very basic ways to access a remote file. Yes. Is there a need for communication in both models? Is that your question? Oh, okay. So your question is, what does it mean to say the need for communication is a downside? So all this is saying is there is more network communication here because every request is a network operation. Here only the initial operation of bringing the file and then sending the final update or some intermediate updates are network operation. All other accesses are local operation. Okay. Yes, question. Okay, question is, how are you going to handle consistency in the second case if multiple clients are going to send multiple updates at the same time, right? That's your question. So first of all, if multiple clients are actually accessing the same file and trying to make update, okay, that distributed application should have implemented locking at a higher level because this shouldn't even be happening to begin with. Okay, if there are multiple writes. Having said that, you might have a single writer and multiple readers. Okay, so you might be writing to a file and other clients are reading a file. In that case, you will still have inconsistencies where you made some changes, but those changes have not been sent over and then some other clients are reading. Okay, to handle that, we'll see what NFS does. I mean, there are only some very simple things you can do. Either you have to implement locking at the application level so that readers might have to block until a writer works and so on. If you do not put those locks or synchronization, the file system is not going to care. It will let you search stale data and so on, right? So, or you have to put better consistency implementation. This is not an actual file system. These are just ideas, right? So if you say, I want to give strong consistency, then if you make local writes, you have to immediately send them over. Otherwise, you will not have an up-to-date version. So you can decide how you implement consistency. We'll see what NFS does in just a few minutes. Okay, but you're right. If you have multiple writes, you will have a write-write conflict. You will overwrite each other. That's something you want to avoid typically. Okay, all right. So let's come to stateful and stateless servers. We'll see that by and large, the design of your distributed file system, regardless of what approaches are used, has to make a fundamental choice of, is the server going to keep state about the clients or is the server going to be stateless? So a stateless server basically means there is no information that the server keeps about the clients and which clients have opened what files and so on. Every time a client makes a request, it sends complete information about what it needs from the server, saying, I need this file, I need the 10th block or the 10th byte, here's the byte offset, I need to read 15 bytes, whatever it is that your read or write operation does, every operation sends complete information because the server has not kept any information. Okay? In contrast, in a stateful server, it's the exact opposite. The server keeps track of which files are open currently in this file system, which clients have opened this file, where is the current file offset, so that you can read or write from that point on. All of that information is kept by the server, hence it is stateful, because it gives state about all of these clients. Okay, so you can either make the server stateless or you can make the server stateful. Okay, so these are fundamentally two ways you're going to implement. Now, if you make the server stateless, it is going to be more tolerant to crashes. The server can crash and come back up. There is no state, so there's nothing to lose. Okay, another client can then make another request after it's come back up. Everything works as is. Okay? On the other hand, if you had a stateful server and you had 10 files open, server crashed and came back up, that state is gone. Now the client says, give me the next 10 bytes. Server doesn't know where the file offset was. All of that information has disappeared. Right? So it is less tolerant to failures. Okay. Having said that, there's information, so you can actually have a little better performance with stateful servers because requests are more compact. In stateless server, every request has to have all the information needed to access the file because you have to specify everything all over again. Okay, here's some information about the file offset and the fact that the client actually has permissions to open the file. All of that is already being checked. Okay, you don't need to keep checking it for every request, so you can get slightly better performance. Requests are shorter. Okay? In some cases, you'll see consistency is easier to achieve because you know precisely which clients have opened what files. So if file changes, you can propagate consistency messages. All of that is easier to achieve. Okay, and we'll see that you can also make idempotency easier. We'll get to idempotency as well. Idempotency simply says that if you make the same operation multiple times because of timeouts and so on, you want the end result to be the same as if the operation was done once. Okay? An idempotent operation simply means regardless of how many times you make the operation, okay, you get the same result. Okay? So if essentially you are doing RPCs, say, you say append this string to the end of the file. Okay? Maybe you don't get a response from the server. You might think the request got lost, you retransmit. Say append the same string again. The operation is performed twice at the server, that's not idempotent because that string will get appended twice. An idempotent server will ensure that regardless of how many times it receives the request, it actually gets executed only once. Or the end result looks like it was executed only once. So you want to ensure all of these kinds of things because there will be message loss, there will be network problems and all kinds of things. Okay? So that's something you want in your file server as well. Okay, so with that background, let's talk a little bit about NFS. Okay, so NFS essentially stands for Network File System. It's a very old file system. It was one of the earliest ones that was designed, that was a distributed file system. Okay? And it was specifically designed to take the disk or the file system on one machine and make it accessible on a second machine or some number of client machines. Okay? Now, the way you want to keep NFS in mind is it's not really a new file system. Okay? It's a layer that sits on top of an existing file system. Okay? It's a way to share an existing file system over a network. That's the way you want to think about it. Because in its core, it's not really a file system the way you think of a file system where it actually is managing the blocks on disk and so on. That's what our file system would do. Okay? What NFS does is you can have whatever file system you have on your machine, you add NFS software on it, it just allows you to take that file system and share it over a network. Okay? So in other words, NFS runs on top of other file systems, okay, but makes them network accessible. So that is essentially what it does. So you should really think of it. This picture is not going to show it to us, but what you should really think of it as, you have a disk, you have a file system on top of the disk. NFS is a layer that sits on top and allows you to export all that file or some subset of that files to other clients. Okay? Now, the way you implement NFS or any file system in an OS is through this concept of a virtual file system or a VFS layer or a VFS switch. Okay? And what does so this is a technique that's not specific to NFS. It's a technique that is used by operating systems to support multiple file systems at the same time. And most general purpose operating systems will actually have the built-in support for multiple file systems. Okay? You will have, let's say on Windows, you will have NTFS on your actual disk. In Linux, you will have ext3 and so on. But you can plug in a USB drive. Okay? That actually has a fat file system. It's a very old file system that was invented in older versions of DOS and Windows. Okay? Completely different file system. Okay? You can insert, if you have a CD drive or a DVD drive, you can insert a CD or a DVD. That's a different file system altogether. That uses something called an ISO file system. Okay? So your OS already comes with built-in support for multiple file systems. And so how do these file systems coexist inside the OS kernel? So that's essentially where this virtual file system layer switch comes in. Okay. So what happens is regardless of the fact that there are multiple file system implementation, from a user's perspective, all this is hidden. Okay? The user doesn't know that, okay, this file is actually on a USB drive, so it has a different structure underneath, or this file is stored on my SSD, so it has a different structure underneath. All you see is an abstraction of a file. You see the ability to open the file, read the file, write to the file, close the file. That abstraction is the same regardless of the internal implementation of the file system. Okay? So there has to be a way by which you can take specific implementations of different file systems and export a common interface to the user or to applications, regardless of what the internal implementation looks like. That is what this VFS layer is going to do. So as the name suggests, a virtual file system. Here, the word virtual doesn't mean there's any virtualization. Okay, there's different concept altogether. It just says that this is a logical layer, okay, that exports a common interface above to users. Okay, so here is your client. Okay, of course, in this case, we have NFS, so there's a server as well. But let me first explain what the VFS layer is. So when in the VFS layer, you say you open a file, okay, and you give a file name. Okay, you will say /user/local something something. You give us file name. Okay. So the OS is going to parse that name and try to figure out which device is that file on. So maybe there are multiple, there may be a USB drive plugged in, which is not shown here. There is an actual disk, and there is NFS. Okay. So depending on where the path name leads you, it will come here, and the virtual file system layer will forward that request to the right file system module inside the kernel. Okay. If that file happens to be stored on the USB drive, you will send it to the FAT implementation module. If it is on your NTFS, you will send it to the NTFS module, which is here is a local file system. If it is a remote file, in this case NFS, that is going to go to the NFS implementation inside the kernel. Right? So this is really a forwarding layer that looks at where is that file stored, what type of file system is it stored on, and it will invoke the right file system implementation, because there are multiple of them inside the kernel. Here in this picture, only two are shown. There's a local file system, which you can think is something like NTFS, and there is the remote file system, which in this case is NFS. But in reality, there will be many of them. They are all sitting inside the kernel. Each of them is managing some storage hardware. Okay, and then depending on what type of file you open or where it resides, your open read write calls are going to be forwarded through the VFS layer to the right implementation. Okay. So you are abstracting all of the implementation specific details using the VFS layer. Okay. So we will use that same concept for NFS. Okay. So in this case, the client essentially sees files that are stored on your local disk. It also sees files that are stored on this remote disk, okay, through the NFS. Okay. So now from a user's perspective, user can't actually tell just by looking at a file name, is it a local file or a remote file? And you shouldn't even need to care. You just open files as if they were files. And then inside the OS, if it's a local file, that request for that file or a read writes go to the local file system implementation. If it's a remote, it will come to NFS client. NFS client is essentially going to make that into an RPC request, send it to the server. Okay. So it will be received by the NFS server. The NFS server will essentially go up to the file system layer, the VFS layer, and then send that request to that local file system on that server. The local file system will actually perform that operation, whatever was sent by the client, and then the results are going to go back. Okay, so essentially you are using RPCs to communicate, but the important part is this hiding all of this from the user. The user is just opening files, regardless of whether they're local or remote. You can just open files in your editor, or you can compile files. It doesn't really matter. All this is happening under the hood. Okay. So for any distributed file system, you essentially want to present the abstraction like they're local files, and this is how you achieve it. Okay. Any questions on this? Your question? Yes. Yeah, question is, can any machine be the client and the server at the same time? That is indeed true. So here is a server machine where these files are actually exported to some other machine. So this server machine will support read, write, open calls that are coming from another client. But you can have local applications running here that can also access that same files, right? So because in that case, they're local files. So So you are essentially a client and a server at the same time. Okay. Any other questions? Okay. So that's a very high level overview of NFS. This table here, you had another question? Yes. Okay. Okay. So question is, if you have NFS, you opened a file that's actually stored on the server on a client machine, and then you're writing maybe some code and periodically saving the file. Okay, when does the file updates, writes get to the server? That's your question, right? So the answer to that is actually dependent on the distributed file system implementation and what consistency model it will support. Okay. Here we are talking about NFS. Okay. NFS, as you will see shortly, gives weak consistency guarantees. Okay. So it is basically going to keep writing to a local cache. Okay. And then periodically it was going to send all of that data to the server. So it's not immediately going to send things to the server. So it takes up to 30 seconds for any writes, any saves you have made on your editor to get propagated to the server. For that period of time, whatever is on the server, the version of the file is out of date with respect to what is on the client. Okay. If you wanted tighter consistency guarantees, every write should have been immediately sent. That's not what NFS does. For performance reasons, files, all writes are actually made to a local cache. Okay, and then that cache is flushed periodically. Okay. Okay. Question is, if you're fetching the file, will you fetch the whole file or will it do one block at a time? Different versions of NFS, you will see do things differently. Okay, the basic version, when you open a file, okay, it will fetch whatever blocks are right. Now, if it's an editor, you essentially read the whole file into your editor. So in that case, you actually said read to, commands for all blocks of the file and got them. But it may be a giant file and you can only open one block of the file and only that block will be fetched. You will not fetch other files. Editors by default just load the whole file. It doesn't matter. So then in that case, that's the application is reading the file, but you don't have to. You can only read blocks and modify those blocks. Okay. All right. So what this long table shows is a list of RPC calls that are the interface exported by NFS. Okay. Each of this row is one RPC call that NFS supports. Okay. So collectively, that's your NFS file system interface. Okay. I'm not going to go through all of them, but you will see there are familiar calls. The last two are read and write. Okay. This is how you are going to read and write blocks of the file. Okay. To read a file, you send a set of read requests, read each block, and you get the whole file. To write, you can write to a specific block that you updated and so on. Okay. And then you will see that there are create and there is open, close, and so on. So, and there are many others that are directory operations. I'm not going to go through them here, but I do want to point one detail here. Okay. There are two columns. The second column and the third column are basically labeled version 3 and version 4. Okay. So that's essentially NFS version 3 and NFS version 4. Okay. So NFS now is in version 4, but the NFS version 3 of NFS is still in wide use. Okay. Now until version 3, okay, NFS used a stateless model. The server never kept any state whatsoever. There was no state at the server. Okay. Every time a client has to make an RPC request, you send every information, all the information you need to perform that stateless operation. Okay. Starting version 4, okay, NFS became stateful. The protocol was modified to allow state to be kept at the server. Okay. And so that has some implications in what calls are supported. Okay. So in particular, if you look at the open call, okay, you'll see that most of the time in both rows, it will basically say the same thing. But there are some rows that are not going to be same for version 3 and 4. In particular, if you look at open, okay, so you will say that version 3 does not even support open as a call. Okay, and version 4 does, because open is a stateful operation. You open a file, you get a file descriptor, and then you use that file descriptor to make subsequent requests. That's the notion of what open does. Okay. But if the server is stateful, it doesn't make sense to have an open, because that file descriptor that's returned is useless because there's no information that's kept at the server. Okay, the client will still do an open, but it's not going to go to the server. You're going to just do some local thing in the NFS client and return it. Okay, you might check for some permission access and so on to see if the open should succeed or not, but you're not going to keep state at the server. So version 3 did not actually officially support an open call, but you did have something called a lookup. So if the client did an open, you would do a lookup saying, is this user allowed to access the file? Do they have permissions? If so, the open succeeded, otherwise it didn't succeed. But you never made an actual open request at the server and kept state and so on. Okay. But you will see in version 4, you actually do support open, because now you made the server stateful. So your open requests actually go to the server opens the file, returns a descriptor, keeps state and so on, like a normal file system. Okay. So there are these differences. So NFS was one of these file systems that always used to go with the stateless approach until you got to version 4. And you will see that keeping state allows you to do certain things that you cannot do with a stateless server. Okay. So that is, as a result, some of these calls are different, open being the most important one. Okay. And then reads and writes are supported in both cases, obviously. And so are many other operations. Okay, with that background, let's look a little bit about how RPCs work and so on. Okay, so here is a time diagram that shows how an open followed by a read is actually implemented in version 3. Okay, so version 3, the open will become a lookup. You will send a lookup request saying, here's a user, do they have permissions and so on. Okay, the answer is going to be either yes or no after the RPC request is performed. Okay, and then if it succeeds, then you can actually make a read request. So these are two independent RPC calls. Okay. Now in version 4, not only do you have a lookup followed by an actual open and then a read, but a version 4 also has the notion of a compound RPC. A compound RPC allows you to batch multiple requests into a single RPC. It's not something we have seen thus far. So this is like a batch RPC. One RPC request, one message has multiple calls embedded in it. Okay, so as you will see, this RPC request has a lookup, open, and read. All three operations are actually sent as one big RPC request. Okay, they are actually treated as individual operations at the server side. You perform all the operations, and all the results are sent together. Okay. Now, compound RPC allows you to reduce the network messages. Okay, the number of round trip messages you have to send is reduced. Okay, but of course, it will take longer to make the execute the RPC because there's more to execute. So this is a feature that was introduced in version 4, but of course, version 4 also added stateful features, which is why an open and a read at the client side done by the application becomes a lookup and a read at the NFS level in version 3. But in version 4, you get what you expect, which is you look up saying, do I have permissions? If so, I go open the file and then you can perform whatever operations you want. Okay, so just a simple example to show some differences between version 3 and version 4. Any questions here? All right. So with that, let me talk a little bit about this notion of mounting and so on in NFS. So the way you actually, you have a question? Yes. All the updates are done at the server. Yes. We will see that version 4 actually has that feature also, but the default is always send all operations to the server. That is the NFS default. But there is optimization where you can actually make things to a local cache and so on. Having said that, if you are asking, does NFS keep a cache? In all cases, it does keep a cache, right? So this is happening after the caching part is done. So let's say you read a block of the file. Okay. So initially, it is going to basically do that lookup and read. But the NFS client will also keep a memory cache of whatever has been read from the server is kept in the memory cache. The client makes the read request on that exact same block. It will serve it from the cache, and this RPC is not even going to happen, right? So caching is independent of this. This is just assuming after you have figured out whether a data is cached or not, this is what you will do. Okay, so caching is still present in both. Other questions? Okay, so let's talk about this mount protocol. Mount protocol is a way by which an NFS client gets access to a remote file system. Okay, if just because of an NFS client, you can't go and access whatever files you want on the server. Okay, the server has to decide which directories are actually accessible to a remote client, and you can even control which clients can access them. That way, you don't make your clients files accessible and some random client starts accessing your files. You need control over what files are shared, who gets to see those files. Okay. So all of that is done through a protocol called a mount protocol. Okay, mount protocol essentially is establishes a mapping between some directories on the remote server and how they can be accessed on the local machine. Okay. In the Windows world, this is like making a network drive. Right? So you can do an E drive and an F drive by actually establishing a mapping with the server. In the Unix world, this is called mounting. So you have, let's say, here is the server. Okay, this is essentially a directory. Okay, so you can take this directory and you can mount it on a client. Okay, and so now that directory becomes accessible to that client using that path. Okay. If you logged into the Ed Lab, you will see that your home directory is accessible on any machines. This is because the home directory resides on a NFS server, and that home directory is mounted on all of these clients. So if you actually log into one of the Ed Lab machines, your home directory is accessible, but it is actually stored remotely. And this is done using the exact mount protocol and the exact thing that's shown here, where this home directories are actually mapped to all of the clients. So when the client logs into any of the client machine using, say, SSH or through console access, their files are available as if they are stored locally, even though they're actually stored on a remote machine. Okay? That mapping is established at boot time. When the machine boots up, you establish this mapping so that that mapping allows you to access those files. Okay? You can also construct that mapping on demand, but typically that mapping is going to be performed at boot time. Okay? So this is essentially called mounting. Okay? So you have to keep the system administrator has to create a mount table saying these are the files that I'm going to volumes that I'm going to take from the server, and this is where I'm going to make them accessible. So your home directories will be in /home/user, right? As an example, that is the mapping that the system administrator has decided, saying take your home directories and put it in /home, okay, mount it in /home. Okay, so that's our mount protocol. But there are lots of interesting questions that arise about mounts, which is what happens if the volume you are exporting from the server itself has mounts in it. Are you going to allow recursion and so on? Okay, and here is an example to first explain the problem, and then we'll try to understand what is the implication of doing this. Okay, so in this figure, the previous figure, you had one server and two clients. Okay, in this figure, there's a single client. There are two servers, the server A and server B. Okay, server A has taken this install directory, okay, and all the files in it, and it has exported it, which means it is allowing another machine to mount it. Okay, so this install directory is now mounted on this server A at this location. Okay, packages draw. Okay, that's where it is. And then the /package directory, which is the top level directory in the outer dotted line, is itself exported to a client. Okay, so the client has actually mounted /packages from server A. Okay, it's here. So now the question is, if the client tries to actually look inside /packages directory on the server, should the files that are mounted here from a third machine be visible or not? Okay? Because if you go into /package/draw on this from this client, all of these files are not resident on A, they're actually resident on B. Because you mounted this volume inside here, and then you took a parent volume and exported it and mounted it. So the question is, should you actually follow this mounting recursively or not? Right? So there are different answers to that question. Until version 3, recursive mounting was disallowed because that's a security risk. Okay? Because server B trusts A. So I will let you access my files. Okay, but now if you let server A export that to whoever else, you lost control of your files because A can export it to some other machine You don't trust that machine. You only trusted server A. A went and exported your files to somebody else, right? So now you lose control over who gets access to your machine or your files and so on. So until version 3, okay, this transitive or recursive mounting was disallowed, which means if you have slash packages here, if you try to go into draw, you will get an error. You won't see those files because those are actually stored on a different server altogether. Okay? So that was explicitly disallowed. And the only way you could make it work is you have to then take slash install here and then do a second mount here. So you mount the upper volume from A and the client has to mount the inner volume from B, which means that B actually has control. If B trusts this client, it will allow it to mount it. Otherwise, it will say no. But you are not going to get access to those files simply by accessing server A. That is disallowed. Okay. Is that clear what I said about recursive mounts and why this is an issue? Now, version 4 onwards, you can actually support recursive mounting so long as you take care of the security issues. So you can say, so long as B trusts the client, you can allow this packages the volume to be mounted there. And if you try to go into the slash install directory, what will happen is the request will come to the RPC request will come to A will make another RPC request to B, and the results will go back. But you have to still establish a chain of trust for that to happen. You can't arbitrarily export to some client that the server doesn't trust, in which case it will not support that request. Okay. So these are all issues that don't come up when your local files. When you share these files across machines, you have these issues of, okay, who do you share it to? Do you allow resharing? So that's essentially what is happening here, right? So in the simple answer is you shouldn't allow it. That keeps your security policies in your control. You have control over who gets to access your files. Okay, but if you allow resharing, then you have to still establish some policies that says who gets to access it if it was reshared and so on. Okay, so that is crossing mount points. And then NFS also has this notion of auto mounting, which is called mount on demand. If you have lots of volumes you are mounting, rather than mounting them all at boot times and they're just sitting there idle because users are not accessing them, you just establish the mapping and then you mount on demand. If the user tries to access a directory, you immediately go to the server, mount it, and then make it available. And if there's an idle time, you unmount it. Okay, this way you don't use up all sorts of kernel resources, keeping some mappings, and then the mappings are just taking up memory resources and so. Okay, this is a popular option actually for home directories. Okay, you might have thousands of users who have accounts on a server. Okay, if every client has to mount all of those volumes or home directories, that's a lot of mounts. So what you do is you have each user. Okay, so you have users, maybe you have user Alice and Bob and so on. Okay, so you don't take each of the directories and mount them separately on a client machine. If the user logs into that machine, you can say user has just logged in, then go mount their volume on demand. Okay, and when the user logs out, you can essentially unmount it. Or if the user will CD into a volume that's not mounted, okay, you can look up the table dynamically and mount on demand. Okay, all of this is called auto mounting, where you establish this network volumes mounting on demand. Okay, and then you unmount, which is used to basically save resources. Okay, any questions on this? All right, so now let's talk a little bit about NFS implementation, and then we'll get to the NFS version 4 and how the stateful nature of version 4 allows for features that were not available till version 3. Okay? So the first thing to keep in mind is, as I said, NFS is not a real file system. It's a layer that sits on existing file systems. Okay? So what that means is for NFS to allow any current file system to share its files with some other client, it has to support a wide variety of file systems underneath. Okay? As a result, the basic requirements of what a file system should support to be compatible with NFS, okay, is a very minimal set. Okay? Because you have to have some features that the file system supports for you to have, say, okay, is NFS compatible with it or not? Okay. So NFS designers came up with a very small set saying, so long as the file system supports these requirements, you can make it work with NFS. Okay. And those requirements are referred to as file attributes. What should the file system support on every file? Okay. So by default, you need a file system to have every file support these 4 things. Okay. So it should keep some information about the type of a file, which is it an actual file or a directory or a symbolic link? You should keep track of the size of the file. You should keep track of some way to see if the files has changed. And there should be an ID, which is a unique identification of the file. So long as your file system supports these 4 attributes, it is compatible with NFS. Right? Now, if you look at this, you will see that lots of things that you normally expect a file system to support is not a requirement under NFS. NFS doesn't require that a file have an owner, okay, because it's not a mandatory attribute. We'll see that it's a recommended attribute, but not a mandatory one. Okay, and lots of other things. Okay, so all you need are these 4 things, and it's compatible. So what this means is very simple file systems. Like you can take a USB drive. If you think about it, the file system on a USB drive doesn't actually have an owner. It's meant for sharing. If you have an owner and you give your USB drive to somebody else, they can't read it if you are the owner and you didn't put read permissions and so on. So it doesn't actually have many of these things. So even those very simple fat file systems are compatible with NFS. So it's been written in a way that makes it widely compatible, which is why it's widely successful. There's very limited requirements on what a file system needs to support. Okay. So here are other attributes saying these would be nice to have. It will make NFS work better. And here you will see usual things like, okay, access control list. What are the permissions on the file? If you support it, I can actually make the clients see it. Okay, who's the owner of the file? Okay, what is the last time of modification? What's the timestamp? All of these things that you expect are not required, but they are recommended, which means it makes NFS work better. Okay. But even if the file system didn't support these features, you can still make it work over NFS. You can export it, some other client can access it, and so on and so forth. Okay. So this is all mentioned in the NFS protocol. Okay. So protocol says here the NFS client or the server will work with file systems that have at least these 4 mandatory attributes, but these other recommended attributes would make it work better. Some of these operations will just work better. Okay, your question is. Okay, question is, does NFS work with data that is replicated? That's your question, right? So we will probably not get to this in the lecture today, but NFS has the notion of replicated servers. Okay? So you can have multiple machines. The same directory is replicated on multiple machines. Okay, this collection of NFS server collectively acts as a single logical server. Okay? In this case, writes are sent to all, and reads can be sent to anyone. Okay? That allows for fault tolerance. If one server goes down, okay, the other servers can still serve your files. Okay? So it is not that NFS supports a file system that is using replication, but NFS itself can use a replicated file system and actually provide better fault tolerance. So it has support for a set of servers that all serve the same volumes. Okay, that's the way you want to think about it. Okay, so let's move on. So now let's talk a little bit about consistency and semantics. Okay? So there are 2 pictures here. The first picture is a local machine. There is no NFS, there's no remote file system or anything like that. Okay, you have a file. Okay, the file has 2 characters initially, A and B. Okay, the file has just two of these, and there are 2 processes accessing it. Okay, so here process A opens the file and appends C, the character C to the file. Okay, so the contents of the file become A, B, and C. Okay, if process B comes later on and tries to read this file, it's going to see a file that has A, B, C in it. That's how local file systems work. You write to a file, all the changes are immediately visible to every process. Okay, that's what we expect to happen normally. Okay, here is what happens in an NFS case. Okay, here's your file server. the same file A and that contains A and B stored on the server. Okay. Process A, in this case, is running on client 1, and the process B that we saw here is actually running on a different machine. Okay. You can see what happens with the same sequence of operation. So process A opens the file, and it writes C to the file. Okay. NFS assumes that when you make writes to the file, they are not immediately sent to the server. They're sent to a cache. Okay. The write will return, and at some later point, the NFS cache is going to be flushed. Okay. So you already wrote B. You already wrote C. So the file has changed on machine 1. So process A sees those changes because it wrote it. But if B comes along and tries to read that file, it's going to get an old copy of the file. Okay. So this is fundamental to how NFS is designed. Okay. So what that means is, if you have two processes that are accessing some shared file on a local machine, okay, you will see one behavior. Now, if that file is actually moved to a NFS server and these two processes end up on different machine, the same set of operation may get you a different result because cache consistency is weaker in case of NFS. If NFS implemented strong consistency, if B read that file after A is right, it should still have seen A, B, and C. But that's not what you see, right? Because it uses caching as a performance optimization and it weakens consistency. Okay. So this can cause problems if you don't, if you're not careful. If you have multiple processes trying to read and write, okay, you might see outdated version, okay, unless you do something at the application level. Okay. So this brings us to what semantics NFS provides. So the semantics I showed you, which is what happens on a local machine, they're referred to as Unix semantics. Okay, these are cache consistency semantics in the file system world. Okay, Unix semantics says every operation on a file is instantly visible to all other processes. If I make an operation, it's visible. Okay? It is equivalent to strong consistency, but in Unix world, we call them Unix semantics. Okay? Another one is called session semantics. Session semantics says that when a file session closes, all the changes I made are immediately visible. This is somewhat like what NFS will do, because if you close the file, it will immediately flush all your changes. If you don't close the file, it will keep flushing every 30 seconds. There's a timer. It goes off every 30 seconds. You take all your dirty blocks and you flush it. Okay? So essentially, you are getting somewhere between Unix semantics, where files are immediately visible, and session semantics says from open to close, don't bother sending anything to the server. When you close the file, send all your changes. That's what session semantics is. Okay, NFS is doing something in between. Okay, it's not waiting till you close the file, but it's not sending things immediately either. So you essentially have a delay where you keep things in a cache and you keep sending only periodically. Okay. And the protocol, NFS protocol, does not tell you what kind of cache consistency to implement. Okay, this is left to the implementation. This is why most implementations, okay, this is not an artifact. What I said is not an artifact of the NFS protocol, because NFS protocol did not say what consistency semantics to implement. Okay, the standard doesn't say anything about consistency semantics. So most implementations said, if they don't want strong consistency, why should I implement it? It's too expensive. It hurts performance. Let's give weaker consistency. Okay, so it implemented this caching and flush model every 30 seconds, gives weak consistency, but causes all kinds of other problems. Okay, if you have multiple applications on different machines, sharing files, reading and writing files, changes are not immediately visible. You can't write to the end of a log and then read immediately that log file. If it's stored on the server, that log entry may not even show up. Right? So you will have all these change issues. Yeah. And then for other file systems, there are other semantics which are not specific to NFS. There's one called immutable files. Immutable files says once you create a file, you can't modify it. To modify it, you have to create a new version of the files, because the files are versioned. Okay. Once you create a version, it can be only read. If you want to modify it, you increment the version. So you can actually have a whole set of versions. So there are versioned file system that will do this, because that allows you to roll back to a previous version and so on. So each version is immutable. But if you modify it, you create essentially a new version. Okay? And then you have transactional semantics, which say that all my changes are essentially done atomically and so on. This is what databases do. And some file systems have started providing transactional semantics as well. Okay? Very few, because that is hard to implement. You have to give asset properties and so on. So most of them essentially give very weak guarantees, which are eventual consistency, weak consistency, the session semantics, and so on. Is this clear? Okay. So I will say a few words about version 4. Okay, why was version 4 made stateful? Okay, the reason is, if you don't keep state at the server, it prevents you from doing variety of things that have utility. Okay? One such thing is adding locks to a file. Okay? Many file systems, local file systems, not remote file systems or distributed file systems, many file systems actually support a concept of file locking. Just as you have a lock on a shared data structure, you implemented locks in your labs and so on, and file systems actually have built-in support for locks. You can actually take a write lock on a file, which means that another file or process, if it opens that file, okay, to read or write, it will be blocked. Okay? It will basically that your operation will just wait there until the lock is released. Okay? So the locking is very similar to the locking you use when you have threads and so on, or the way you use them in your lab, but implemented inside the file system. Okay? But the thing you want to keep in mind is the lock is essentially a stateful object, because the fact that whether the lock is free or in use essentially is state. Okay? If you have a stateless file system, you cannot implement locking. Yes. If I have a stateless NFS server, I say lock this file, server will say fine, and then there is no information because it's not keeping any state. So if another client tries to access it, it does not know that there was even a lock grabbed on the file. So you cannot implement file locking. Okay? Which is useful for a variety of other sharing applications. So one of the reasons you have state is you can do things like locking. So NFS version 4 actually made it stateful. So now you can implement locking using NFS, just as you have locking in a local file system. Okay? So this allows you to now take a lock on a file. You can lock a range of the file, saying lock byte offset 10 to 15. So only those bytes are locked. The rest of the file is still accessible. Don't have to grab a lock on the entire file. You can grab a lock on the range of the file. You can essentially remove a lock on the range of the file. So there are all kinds of locking operations performed. Okay? The important thing is locking does not have to be done at an entire file level. You can lock parts or blocks of the file or some bytes of a file and so on. Okay? It is very useful when you're implementing databases on your file system. Okay? Because databases have to implement locking. And this is one way your database can actually use the file system locking capability to implement higher level locks when you have transactions and so on. Okay? So this is one of the reasons file systems actually support locking. The good use cases, it makes database writing applications easier, writing databases easier. Database locking can simply use OS locking facility in the file system. It doesn't have to implement its own locking and so on. Okay? So this is what version 4 will support, but until version 3, because it was stateless, you could not support it. Okay? So that is NFS locking. I'll say one more thing and then we will end today. The last few slides you can look at next time. Okay? So there is, in addition to locking, there is also a way to get what is called reservation. So you can have the equivalent of read and write locks as well. Okay? In the previous case, the locking was you locked, it was like a normal lock. Right? You locked a range of bytes and everybody else is blocked from accessing it. This is like a normal lock. But NFS also has this notion of a read and a write lock, where if you get a read lock, okay, you essentially will only allow certain operations. If you have a write lock, you allow certain operations and so on. Okay, so the way you do this is you essentially ask for what is called a denial state, saying what operation should you deny for other applications. So if you say essentially deny write operations, okay, then you essentially hold the equivalent of a write lock where no one else will be allowed to write. Okay? If you say deny read operations, then you will basically prevent other users from reading the file. If you say deny both, that's like grabbing a normal lock. It says no one else can do any operation, a read operation or a write operation. Okay? So you have this notion of a denial state where, so if some user application has a read denial on a file, then the read operation will fail. As you can see that, but write operations are allowed to succeed, right? Because you have only said deny read operation. If you have the denial state is write, which means I am denying write operations on the file. Okay. If some other user comes and tries to do a write, you will see that it will fail. But read operations are succeeding. Okay. But if the denial state is both, which means deny both, then all operations that are performed by any other application will fail. Okay. So it's not exactly the same as grabbing a read or a write lock. The read lock, reader writer lock, there are multiple readers and single writer. That's not exactly what these reservations do, but it allows you to say what operations are permitted by others if I am accessing these files and what should I deny. Okay, if you want to be safe, you should deny both. That way you have exclusive access to the file. But you can just say, I will deny reads, I will deny writes, and so on. Okay. This concept is called share reservation. So you can make a reservation on a file and then prevent someone else from performing certain operation. Okay, it's a type of a locking, okay, but it's not different from grabbing exclusive locks. Okay. So since we have run out of time, let's stop here today. We'll continue next time. Okay.